All right, we have seen where neural networks are making waves: medicine, space, driving, storytelling, and even more of philosophy. Kind of. But before we dive into building neural nets ourselves, we need to step back and revisit some key ML concepts. Think of this next section as a tune-up. We'll go over supervised and unsupervised learning, loss functions, models, and how we train them, because neural networks don't exist in isolation. They sit on top of decades of machine learning. So let's build a foundation before we start stacking layers. Here is a quick checkpoint. This is where we're in the grand plan. We just wrap up the history and recent developments. Now we're into the review of machine learning basics. This is a launchpad for everything that follows. So if it feels familiar, good, you're ahead. If not, don't worry, we'll take it slow and build it back up. Machine learning comes in many flavors, but the two main types are supervised and unsupervised learning. In supervised learning, we give the model label examples like photos tag cat or not cat. The model learns to predict the label based on the input. In the plot here, the inputs are two features, x1 and x2. Each point is labeled by color, red or blue, which is the target or output. The model's goal is to find a boundary that separates the classes. That dashed line, that's the model. It has learned from examples where the reds tend to be and where the blues tend to be, and tries to draw a line in between. Unsupervised learning, no labels. It is like dropping the model in a room full of jigsaw puzzle pieces and telling it, good luck. It tries to find structure, clusters, patterns, correlations, without even knowing what the right answer is. We mostly focus on supervised learning in this course, especially for classification and regression tasks. So how does supervised learning actually work? There is a simple pipeline behind it. First, we collect labeled data, our training set, made of input-output pairs. Then we choose a model. That could be linear regression, a decision tree, a neural network. It depends on the task, the complexity, and how flexible we need the model to be. Next, we define a loss function. This tells us how far off our predictions are from the true values. And finally, we train, which means adjusting the model's parameters to minimize the loss. This is usually done with gradient descent, as we will see soon. Most models we use are parametrics. They have a set of parameters, usually denoted by W, that we learn during training. Well, that's a core workflow. Label data in, optimize model out. Now, let us look at each step of the supervised learning pipeline in more detail. Step 1, get labeled data. No shortcuts here. If the labels are messy, missing, or biased, the model will learn that mess. It's the old saying, garbage in, garbage out. So spend time cleaning and curating your dataset. It matters more than the fanciest architecture. Step 2, select a model. Are you doing regression, classification, object detection? Your choice here shapes everything, from the architecture to the loss function. For this course, we'll focus mostly on models used in classification and regression. Step 3, define a loss function. This is how the model measures its own mistakes. For regression problems, we might use mean square error. For classification, binary cross-entropy or categorical cross-entropy, and sometimes hitch loss are common choices. The loss function turns intuition, how bad is the prediction, into a precise number we can minimize. Final step, minimize the loss. This is where learning actually happens. The most common method is gradient descent, a way to adjust the model's parameters to make the prediction better. We talk a lot more about how gradient descent works, but for now, think of it as trial and error. The model makes a guess, sees how wrong it was, and updates itself to do better next time. Over time, it makes fewer mistakes, and that's what we mean by learning in machine learning. And with that, you have seen the full workflow. The same pipeline used in everything from simple regression to massive neural networks.